Look up at the night sky, and what do you see? A vast, endless expanse dotted with stars, planets, and galaxies. So much beauty, so much wonder. Yet here's the humbling truth. For all our telescopes, probes, and brilliant minds, the universe still holds mysteries that leave even the greatest scientists utterly stumped. Think about that for a second. We've sent robots to Mars, photographed black holes, and mapped the cosmic microwave background, the afterglow of the Big Bang itself. And yet, despite these staggering achievements, space still whispers questions we can't answer, secrets it refuses to surrender. What if I told you there are at least 30 monumental riddles about the cosmos that keep astronomers awake at night? 30 gaps in our understanding so profound, they challenge everything we think we know. From the strange behavior of dark matter to the eerie silence in our search for alien life, these aren't just scientific puzzles. They're doorways to realms of possibility that could rewrite physics, redefine reality, and reshape our place in the universe. And here's the wild part. Some of these mysteries might never be solved in our lifetime. They're that deep, that baffling. So why does this matter? Because every unanswered question is an invitation, a call to explore, to dream, to push the boundaries of human knowledge further than ever before. Imagine standing on the edge of a cosmic cliff, peering into the unknown, wondering what lies beyond. That's where we are right now as a species, and today we're diving headfirst into those enigmas, unraveling the biggest unsolved questions about space that still leave scientists scratching their heads. Buckle up, because by the end of this journey, you'll see the universe in a whole new light, and trust me, it's even stranger than you think. Take the matter you can see, the stars, planets, even your own hands, and stack it all together. Shockingly, it makes up less than 5% of the universe. So where's the rest? A colossal chunk, 27% to be exact, is something we can't see, touch, or even directly observe: dark matter. It's the universe's biggest ghost story, an invisible force weaving through galaxies, bending light, and holding the cosmos together without ever revealing itself. Think of it like this: if galaxies were cars, dark matter would be the unseen tracks they glide on. Without it, stars at the edges of galaxies would fly off into the void, their speeds defying the laws of gravity as we know them. But here's the twist: dark matter doesn't interact with light or any other electromagnetic force. It doesn't absorb, reflect, or emit a single photon. We only know it's there because of its gravitational grip on everything around it, like a shadow puppeteer pulling strings we can't see. Scientists have spent decades chasing this phantom. Underground labs search for hypothetical particles like WIMP, weakly interacting massive particles, while particle colliders recreate high-energy conditions that might conjure dark matter into existence, if only for a split second. Even space telescopes map its presence indirectly, tracing the way it distorts the light of distant galaxies like a cosmic funhouse mirror. Yet after all this effort, dark matter remains a tantalizing what if, a reminder that the universe plays by rules we're still struggling to read. So why does this elusive substance matter? Because it's the scaffolding of reality itself. Without dark matter, galaxies wouldn't have formed, stars wouldn't ignite, and we wouldn't be here to ponder it. It's the silent architect of the cosmos, and until we crack its code, a fundamental piece of the universe's story stays maddeningly out of reach. If dark matter is the universe's invisible scaffolding, then dark energy is its mysterious engine, a force so baffling it makes dark matter seem almost ordinary by comparison. While dark matter pulls the cosmos together with gravity, dark energy does the exact opposite. It pushes space itself apart at an ever-increasing speed, stretching the very fabric of reality. Here's what makes it so unsettling: around 68% of the universe is made of this enigmatic stuff, dwarfing even dark matter's influence. And unlike anything else we've discovered, dark energy behaves as if the laws of physics don't apply to it at all. Picture a balloon inflating faster and faster without anyone blowing air into it. That's essentially what our universe is doing, and dark energy is the reason why. When scientists first noticed this accelerated expansion in the late 1990s, it shattered decades of assumptions. Everyone expected gravity would eventually slow everything down, maybe even pull everything back together in a big crunch. Instead, the universe is flying apart like a cosmic runaway train, and no one knows what's pressing the accelerator. The leading theory, Einstein's cosmological constant, a mathematical placeholder he once called his biggest blunder. It suggests empty space isn't really empty but brimming with a latent energy that drives expansion. But here's the catch: when we calculate how much energy this should produce, the numbers are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in science history. Then there's quintessence, a more exotic idea. Unlike the steady push of the cosmological constant, quintessence proposes a dynamic, shifting energy field that could change over time. Imagine dark energy as a mood ring for the cosmos, sometimes stronger, sometimes weaker. But so far, we've found no evidence it exists at all. What's at stake? The ultimate fate of everything. If dark energy keeps strengthening, it could rip apart galaxies, stars, even atoms in a big rip. Or it might fade away, letting gravity take the wheel again. Right now, we're left staring into the void, trying to decode an invisible force that's literally shaping the destiny of the universe and rewriting the rules as it goes. Picture a galaxy teeming with billions of planets, many nestled in the cozy Goldilocks zones of their stars, not too hot, not too cold, just right for life. With odds like that, the universe should be buzzing with aliens. So where is everybody? That's the Fermi paradox in a nutshell, a question that haunts every search for extraterrestrial life. The math says we can't possibly be alone, yet the cosmos remains eerily silent. Let's start close to home. Mars, our rusty neighbor, might be hiding secrets beneath its barren surface. Rovers like Perseverance have found organic molecules, hints that life could have taken root billions of years ago when rivers carved its valleys. Then there's Europa, Jupiter's icy moon, with its hidden ocean sloshing beneath a frozen crust. The upcoming Europa Clipper mission will skim its surface, sniffing for plumes of water that might carry microbial hitchhikers from the depths. Even Saturn's moon Enceladus sprays geysers into space, offering free samples of its subsurface sea. If life exists beyond Earth, these watery worlds are our best bet for finding it nearby. But the real game changer is the James Webb Space Telescope, peering into the atmospheres of distant exoplanets. It's not just looking for water anymore. It's hunting for biosignatures, chemicals like oxygen or methane that could only exist if something's alive down there. Imagine spotting the faint fingerprint of a forest or an alien algal bloom on a world light years away. Yet even with these tools, the silence persists. No radio signals, no megastructures, not a single shred of evidence that advanced civilizations exist. That's the paradox's sting. Maybe life is rare, or intelligent life self-destructs before it can colonize the stars. Maybe we're the first, or worse, the only ones, or perhaps the truth is stranger. What if we're not listening the right way? From decoding dolphin-like clicks to searching for Dyson spheres, the hunt keeps evolving. One thing's certain: answering this question wouldn't just rewrite science books. It would redefine what it means to be human in a universe that's either impossibly lonely or unimaginably vast. Black holes are cosmic enigmas so extreme they twist the laws of physics into knots. Picture this: a place where gravity wins forever, where not even light can escape, and where time itself stretches and warps like taffy. At the edge of every black hole lies the event horizon, a point of no return. Cross it, and there's no coming back, no signal you can send, no trick to escape. It's the universe's ultimate one-way door, But what happens beyond that threshold, that's where things get truly mind-bending. At the heart of a black hole, according to Einstein's equations, lies the singularity, a point of infinite density where space and time cease to make sense. Here, the rules we rely on shatter. Gravity becomes so intense that the fabric of space-time curves infinitely, and our math simply stops working. It's like a glitch in the cosmos, a place where physics throws up its hands and says, "I quit." But infinity isn't something nature usually tolerates, which suggests we're missing something monumental. Enter the holographic principle, a radical idea suggesting that all the information about what falls into a black hole isn't lost, it's somehow encoded on its surface like a cosmic DVD. Imagine everything that ever crossed the event horizon, stars, gas, even unlucky spaceships being smeared into a two-dimensional imprint on the black hole's edge. It's as if the universe keeps a backup copy just in case. This ties into the infamous information paradox, a puzzle that pits quantum mechanics against general relativity. Quantum theory says information can't be destroyed, but black holes seem to erase it forever. Stephen Hawking once thought they simply evaporated over time, leaving nothing behind, until he realized that would break quantum laws. Now, scientists debate whether information leaks out via Hawking radiation or if it's trapped in some unknown form. Then there's the wild card, wormholes. Some theories suggest black holes might not end in singularities but instead tunnel through space-time, emerging as white holes, cosmic geysers spewing out matter and energy elsewhere in the universe. It's a tantalizing idea, though no evidence exists yet. What's clear is that black holes aren't just cosmic vacuum cleaners, they're laboratories for the most extreme physics imaginable. Solving their mysteries could unlock new laws of nature, rewrite our understanding of reality, and maybe even reveal whether the universe itself is a hologram. Until then, they remain the darkest puzzles in the cosmos, places where the known universe ends and the true unknown begins. The Big Bang is often described as the moment our universe burst into existence, but here's the catch: it wasn't an explosion in space. It was the birth of space, time, and everything we know, all unfolding from a single, unimaginably dense point. Picture rewinding the cosmos like a film reel, watching galaxies merge, stars blink out, and matter compress until 13.8 billion years ago, you reach a state so extreme that our physics textbooks go blank. That's the singularity, a term scientists use when their equations spit out infinities, a polite way of saying, we have no idea what happened here. The classic Big Bang theory nails the aftermath beautifully. Within the first second, the universe expanded faster than light itself, a mind-bending inflation that smoothed space into the near-uniform cosmos we see today. Particles flickered in and out of existence, matter barely edged out antimatter, and by the time the first atoms formed, the universe was already cooler than the surface of the sun. We've even detected the echo of that primordial fireball, the cosmic microwave background, a faint glow permeating every corner of space. Yet for all its success, the theory hits a wall when we ask the obvious: what triggered it? What existed before space-time began? Some theorists propose the universe didn't start from nothing but rebounded from a previous collapse, like a cosmic accordion in an endless cycle of big bangs and big crunches. Others flirt with multiverse ideas, suggesting our universe is just one bubble in an endless froth of universes, each with its own laws of physics. Then there's quantum gravity, where space-time itself might emerge from a deeper, weirder reality, like bubbles forming in boiling water. But the real shocker, the Big Bang, might not even be the true beginning. New physics, like loop quantum cosmology, hints that a previous universe could have contracted to a tiny, but not infinitely dense, state before bouncing into ours. Imagine the universe as a phoenix, dying and reborning in an eternal dance. The problem is, without a theory that unites quantum mechanics and gravity, we're stuck at time zero, staring into the abyss. It's not just about filling in a gap. It's about discovering whether beginning even means what we think it does. Until then, the origin of everything remains the ultimate cold case, a mystery written in the stars but still just out of reach. The universe has a birth certificate, the Big Bang, but what about its death certificate? Scientists have narrowed it down to 3 chilling possibilities, each more dramatic than the last, and all hinging on dark energy's enigmatic behavior. First up, the Big Crunch. Picture the expansion of the universe slamming into reverse, galaxies rushing back together in a catastrophic collapse. If dark energy weakens over time, gravity could finally win the cosmic tug-of-war, pulling everything back into a fiery singularity, a mirror image of the Big Bang itself. It's the universe ending as it began, in a blaze of unimaginable density. But here's the twist: current observations suggest dark energy isn't weakening. It's holding steady, or worse, growing stronger. That leads us to the second option, heat death, also known as the Big Freeze. Imagine dark energy keeping the universe expanding forever, stretching space so thin that galaxies drift apart like lonely ships in an ever-darkening ocean. Stars burn out, black holes evaporate, and eventually, every particle is so isolated that the cosmos reaches absolute zero, a lifeless, frozen wasteland where time loses all meaning. This isn't just cold, it's the end of all possible change, a universe where even atoms stop moving. But the most terrifying scenario, the Big Rip. If dark energy's repulsive force keeps intensifying, it wouldn't just push galaxies apart, it would tear reality itself to shreds. First, galaxy clusters would be yanked apart, then individual galaxies. Stars would explode as the force overcomes their gravity, planets would disintegrate. In the final moments, even atoms and subatomic particles would be ripped apart, space-time itself fracturing into nothingness. It's cosmic Armageddon on a scale we can barely comprehend. Here's the kicker: we still don't know which fate awaits us. Dark energy's true nature is the deciding factor, and right now, it's playing its cards close to the vest. Is it constant, as Einstein's cosmological constant suggests, or is it evolving, growing stronger or weaker over time? Telescopes like the Vera Rubin Observatory are racing to measure the universe's expansion with unprecedented precision, hunting for clues in the light of supernova and the clustering of galaxies. What's at stake isn't just academic. The answer could reveal whether the universe is destined for rebirth, eternal silence, or total annihilation. And the craziest part: we might never know for sure. The universe could be hiding its ultimate fate until the very end, leaving us to wonder, right up until the final curtain falls. Here's a cosmic riddle that defies logic. For every particle of matter in the universe, there should be an equal and opposite particle of antimatter, its identical twin with an opposite charge. When matter and antimatter meet, they annihilate in a burst of pure energy. So why does anything exist at all? Early in the universe's history, these twin particles should have cancelled each other out, leaving behind nothing but a sea of radiation. And yet, here we are, surrounded by galaxies, planets, and coffee mugs made entirely of matter. This isn't just a lucky break, it's one of physics' greatest unsolved mysteries, known as the matter-antimatter asymmetry problem. The answer might lie in a tiny crack in nature's symmetry called CP violation. CP stands for charge parity, a rule that says the laws of physics should treat particles and their mirror image antimatter counterparts exactly the same. But in the 1960s, scientists observed something shocking. Certain particles called kaons broke this rule, decaying slightly differently than their antimatter versions. It was like flipping a coin and discovering it lands on heads just a fraction more often than tails. This minuscule imbalance, discovered at Brookhaven National Lab, was the first clue that the universe might have a subtle preference for matter over antimatter. Fast forward to today, and experiments like those at CERN Large Hadron Collider are hunting for even stronger examples of CP violation, especially in particles called beauty quarks. By smashing protons together at nearly the speed of light, physicists recreate conditions similar to the early universe, hoping to catch matter and antimatter behaving differently in those chaotic first moments. One theory suggests a mysterious process called leptogenesis, where ultra-heavy particles in the infant cosmos decayed unevenly, producing just a bit more matter than antimatter, one extra particle for every billion annihilations. That slim surplus is all it took to build everything we see, but the puzzle is far from solved. The CP violations we've found so far are too small to explain the overwhelming dominance of matter. That's triggered wilder ideas like hidden particles interacting only with antimatter or even parallel antimatter universes we can't detect. Every experiment tightens the net, but the universe keeps its secrets close. Solving this wouldn't just fill a textbook gap, it would rewrite the story of our existence, revealing why there's something rather than nothing at all. Until then, we're left staring at a cosmic scale that shouldn't tip, yet somehow does. Imagine folding a piece of paper until two distant points touch, then poking a pencil straight through. That's the basic idea behind a wormhole, a hypothetical tunnel through space-time that could connect distant corners of the universe in an instant. While it sounds like pure science fiction, the math actually allows for their existence. Einstein's general theory of relativity describes space-time as a flexible fabric, warped by mass and energy. His equations reveal that under certain conditions, this fabric could twist so violently that it forms bridges between separate points, like cosmic shortcuts through the folds of reality. The catch: these theoretical passages require something called exotic matter, a substance with negative energy density that defies everything we know about physics. Normal matter, like the stuff making up planets and stars, creates gravity that pulls spacetime inward. Exotic matter would do the opposite, generating anti-gravity to prop open a wormhole's throat against the crushing forces trying to snap it shut. Think of it like trying to hold open a tunnel made of quicksand. You'd need a material that pushes back against the walls with impossible strength. So why hasn't anyone found one? For starters, exotic matter isn't just rare, it might not exist at all. Quantum physics hints at fleeting particles with negative energy, like the Casimir effect's ghostly vacuum fluctuations, but scaling that up to stabilize a traversable wormhole is like building a skyscraper out of soap bubbles. Even if we could conjure enough exotic matter, wormholes would likely be catastrophically unstable. The moment anything tried to pass through, say, a hapless astronaut, the slightest disturbance could trigger a collapse, crushing them or snapping the tunnel shut mid-journey. Yet the dream persists because the payoff is irresistible. A stable wormhole wouldn't just be a faster-than-light subway for interstellar travel, it could also function as a time machine. Enter one end in the year 2100, exit the other in the age of dinosaurs, all thanks to time dilation effects at the wormhole's mouths. But here's the paradox: if time travel were possible, where are the tourists from the future? The silence is deafening. For now, wormholes remain tantalizing what-ifs, lurking at the edge of theory without a shred of observational evidence. But in a universe where black holes went from mathematical oddities to photographed realities, who's to say we won't one day stumble upon a cosmic backdoor? Until then, they remind us that spacetime is far stranger than it seems, full of twists even Einstein couldn't untangle. One moment, the cosmos is quiet. The next, an unimaginably powerful blast of radio waves streaks across the universe, packing more energy than the sun emits in days, yet vanishing in less time than it takes to blink. These are fast radio bursts, or FRB, some of the most baffling phenomena in astronomy. First discovered in 2007, these millisecond-long cosmic flashes appear without warning, often from galaxies billions of light-years away, and then disappear just as abruptly. They're like interstellar fireworks detonating in the dark with no clear fuse. The strangest part, most burst once and never repeat, making them nearly impossible to predict or trace. But a handful fewer than 5% have been caught erupting multiple times, sometimes in frantic, erratic patterns. One particularly famous repeater, FRB 1211-2, even seemed to follow a rough cycle, flaring up every 157 days before going quiet again. These repeating bursts offer rare clues like breadcrumbs leading back to their sources. Yet even with hundreds detected, the question remains, what cosmic engine could possibly produce such violent, fleeting signals? Leading the suspect list are magnetars, ultra-dense, highly magnetized neutron stars that spin wildly, their magnetic fields so intense they could strip the electrons off atoms from 1,000,000 miles away. In 2020, astronomers caught a magnetar in our own galaxy spewing an FRB-like burst, a smoking gun that at least some of these signals might come from these stellar zombies. But here's the wrinkle. Most FRBs originate far beyond our galactic neighborhood, and magnetars alone might not explain the sheer variety of bursts observed. Their energies vary wildly, with some blasting out 1,000,000 times more power than others. Then there's the wild card. Could some FRBs be artificial? The idea isn't as far-fetched as it sounds. A sufficiently advanced civilization might use ultra-powerful radio beams to propel light sails across interstellar distances, with each burst acting like a pulse from a cosmic engine. The one-off bursts could be accidental leaks from these systems, while repeaters might trace back to deliberate, targeted beams. It's a fringe hypothesis, but scientists like those at the Breakthrough Listen project are scanning FRBs for any signs of encoded patterns just in case. Meanwhile, observatories like CHIME in Canada are revolutionizing the hunt, detecting dozens of new bursts monthly. Each one is a time-stamped message from deep space, carrying hints about the gas it's traveled through and the galaxies it's passed. Yet for all the data, FRBs remain cosmic enigmas, their true nature still just out of reach. Whether they're the death cries of collapsed stars, the hum of alien megastructures, or something we haven't even imagined yet, one thing's certain: the universe loves a good mystery. And fast radio bursts might be its most electrifying one yet. Some particles in the universe move so fast they carry the kinetic energy of a baseball pitcher, but packed into a single subatomic speck. These are ultra-high-energy cosmic rays, atomic fragments screaming through space at nearly the speed of light, with energies exceeding 100 million times anything humanity's most powerful particle colliders can produce. Where do these microscopic bullets come from? And how does nature accelerate them to velocities that flummox even our best physics models? The journey starts with ordinary cosmic rays, mostly protons, that constantly rain down on Earth from space. Most are low-energy relics from stellar explosions, but a rare few are something else entirely. The record holder, nicknamed the "Oh my God" particle, struck Utah in 1991 with the energy of a brick dropped from waist height, all concentrated into a single proton. To reach such extremes, these particles must have been hurled across the cosmos by forces beyond anything we've witnessed. Prime suspects include active galactic nuclei, the supermassive black holes at the hearts of galaxies. As these monsters devour matter, they spew jets of plasma stretching millions of light-years, cosmic particle accelerators on a scale that dwarfs anything on Earth. Another contender, gamma-ray bursts, the universe's most violent explosions, where collapsing stars or merging neutron stars might launch matter to near light speed in seconds. Yet even these titanic events struggle to explain the very highest energy rays we've detected. The real headache is tracing them. Cosmic rays are electrically charged, so interstellar magnetic fields bend their paths like hall of mirrors, scrambling their origins. By the time they hit Earth, they could have zigzagged across the cosmos for billions of years. Scientists have turned to creative detective work, using giant observatories like the Pierre Auger Array in Argentina, which covers an area the size of Rhode Island with detectors to catch the particle showers these rays trigger in our atmosphere. Some rays even hint at gaps in physics itself, At certain energies, protons should interact with the cosmic microwave background, losing steam before reaching Earth, a limit called the Greisen-Zatsepin-Kuzmin cutoff. But a handful of rays blow past this barrier, suggesting either unknown cosmic engines are at work, or our understanding of particle physics needs an overhaul. What's at stake? These particles are nature's ultimate speed test, pushing the boundaries of how energy, matter, and space-time interact. Solving their riddle could reveal hidden astrophysical monsters or rewrite the rules of the universe itself. For now, they remain cosmic enigmas, whispering secrets from the far reaches of space just beyond our grasp. Time slips through our fingers like sand, always moving forward. Yet physics insists it's far stranger than our daily experience suggests. Why does time have an arrow at all? Drop a glass and it shatters into pieces, but those fragments never spontaneously leap back together. This one-way street, known as time's arrow, emerges from entropy, the universe's tendency toward disorder. The early cosmos was a tightly packed, ultra-orderly place, and ever since, it's been unraveling toward chaos, dragging time forward with it. But here's the paradox: the fundamental laws of physics don't care about past or future. Flip Newton's equations backward and they work just fine. So why does time feel so irreversible? Einstein shattered Newton's idea of time as a universal metronome, revealing it as a flexible dimension woven into spacetime's fabric. Gravity slows clocks and speed stretches seconds, proof that time is relative. Yet even relativity treats time as smooth and continuous, like a river flowing at different rates but always moving downstream. Quantum mechanics, on the other hand, paints a radically different picture. At the smallest scales, time might not even be fundamental. Some theories suggest it emerges from deeper processes, like temperature arising from the jostling of atoms. Loop quantum gravity even proposes that spacetime is pixelated, with time ticking in discrete, indivisible chunks. A cosmic stop-motion animation. Then there's the quantum realm's weirdness, where particles can seemingly influence each other instantaneously across vast distances, defying our everyday notion of cause and effect. Experiments with entangled particles show correlations faster than light could bridge, hinting that time's strict order might dissolve at the subatomic level. Could time itself be an illusion, a side effect of our macroscopic perspective? The clash between these views leaves us without a unified theory. Relativity's space-time and quantum mechanics' fuzzy probabilities refuse to reconcile. String theory and other approaches flirt with extra dimensions or hidden layers of reality where time behaves differently or doesn't exist at all. Some physicists argue time isn't a backdrop but a byproduct, like the way wetness emerges from water molecules. Others wonder if multiple arrows of time could coexist, weaving complex histories beyond our perception. What's at stake isn't just academic. If time is emergent, not fundamental, it rewrites our understanding of causality, free will, and even the Big Bang's origin. Imagine a universe where time is a language our brains impose on a deeper, timeless reality, a place where past, present, and future are somehow equally real. Until we crack this puzzle, time remains both our most familiar companion and our most profound mystery, a dimension we inhabit yet barely understand. If you built a model solar system based on textbook theories, it wouldn't look anything like ours. From Jupiter's reckless road trip to Uranus' bizarre sideways tilt, our cosmic neighborhood is full of architectural oddities that defy easy explanation. Take Jupiter, the solar system's heavyweight champion. According to the Grand Tack hypothesis, this gas giant didn't form in its current orbit, it went on a cosmic joyride. Early in the solar system's history, Jupiter likely spiraled inward toward the Sun, bulldozing through the asteroid belt before Saturn's gravity yanked it back out. This planetary pinball left scars we can still see today, like the asteroid belt's sparse population and Mars' unusually small size, both possibly caused by Jupiter's gravitational interference during its migration. Then there's Uranus, the solar system's oddball, spinning on its side with an axial tilt of 98 degrees. Unlike every other planet which rotates like a top, Uranus rolls around the Sun like a bowling ball. The leading theory, a cataclysmic collision with an Earth-sized object in the solar system's chaotic youth, a crash so violent it knocked the planet sideways. But simulations struggle to recreate this without disrupting Uranus' moons, leaving astronomers to wonder if a series of smaller impacts or gravitational tugs from passing objects might share the blame. And don't forget the Kuiper belt, that icy debris field beyond Neptune. Instead of tapering off smoothly, it drops off sharply at about 50 astronomical units, as if someone drew a cosmic fence. This Kuiper cliff makes no sense under classic formation models. Some speculate an undiscovered ninth planet lurking in the outer dark could be shepherding the belt's edges with its gravity. Others propose the young sun stolen sibling, a rogue star that grazed our system long ago, stripped away the outer debris like a thief in the night. These puzzles reveal a deeper truth. Planetary formation isn't the tidy, step-by-step process we once imagined. It's a messy, dynamic ballet of gravity, collisions, and chance, where a single cosmic event can tilt a world, scatter a belt, or rewrite an entire system's destiny. Every anomaly is a clue, whispering secrets about the solar system's violent, unpredictable youth. Until we crack them, our models remain incomplete, like trying to understand a storm by studying only the calm after. Imagine an object so bright, it outshines entire galaxies, a cosmic lighthouse blazing across billions of light years. These are quasars, the most luminous phenomena in the universe, packing the energy of 1 trillion suns into a space no larger than our solar system. Their secret, a ravenous supermassive black hole, millions to billions of times heavier than our sun, gorging on matter with such ferocity that it turns infalling gas into a dazzling beacon visible across the cosmos. At the heart of every quasar lies an accretion disk, a swirling maelstrom of superheated plasma spiraling toward the black hole's event horizon. Friction heats this disk to temperatures exceeding millions of degrees, causing it to glow blindingly across the electromagnetic spectrum. But here's the twist: quasars don't just radiate light. Many fire colossal jets of charged particles at near light speed, stretching hundreds of thousands of light years into space. These jets, channeled by the black hole's monstrous magnetic fields, act like cosmic particle accelerators, shooting matter across intergalactic distances with terrifying precision. The puzzle, even for supermassive black holes, quasars shouldn't be this efficient. Conventional physics suggests only about 10% of infalling matter's mass should convert to energy, yet quasars defy that limit. Some hypothetical models invoke magnetic fields so intense they twist spacetime itself, extracting energy directly from the black hole's rotation through a process called the Penrose mechanism. Others speculate that chaotic turbulence in the disk supercharges radiation beyond our current theories. Then there's the mystery of their birth. Quasars were most abundant in the early universe, a time when galaxies were still taking shape. How did black holes grow so massive so quickly? Did they form from the direct collapse of primordial gas clouds, bypassing the star stage entirely? Or did they feast on dense clusters of stars in galactic cores, ballooning in size almost overnight? Observations of distant quasars, some dating to just 700 million years after the Big Bang, challenge our timelines for cosmic evolution. Even their jet mechanics baffle scientists. Why do some quasars fire narrow, laser-like beams while others spray wide cones of energy? And what determines their erratic flickering, with brightness levels that can swing wildly over days or even hours? The answers might lie in the black hole's spin or the disk's magnetic geometry, but for now, quasars remain both a testament to nature's brilliance and a humbling reminder of how much we have yet to learn. Their light cuts through the darkness of space and time, illuminating the limits of our understanding and the wild frontiers still waiting to be explored. Is the universe infinite, or is there an edge to reality we just haven't found yet? Imagine standing in a cosmic hall of mirrors where every direction you look stretches endlessly or loops back on itself in ways you can't see. The answer hinges on one of cosmology's most elusive measurements, the shape of spacetime itself. According to Einstein's general relativity, the universe can curve in three possible ways, like a sphere, positive curvature, a saddle, negative curvature, or remain perfectly flat. And here's where things get mind-bending. Precise observations of the cosmic microwave background, the afterglow of the Big Bang, suggest the universe is flat too, within a razor-thin margin of error. Flat geometry implies infinite expansion, a cosmos without boundaries where space just keeps going forever. But infinity is a hard pill to swallow. Even if the universe appears flat on observable scales, it might still curve subtly on scales too vast for us to measure. Think of Earth's surface. From your backyard, it feels flat, but zoom out far enough and you realize it's a globe. The universe could be playing the same trick, its true shape hidden beyond our cosmic horizon. Some theorists propose wild topologies, like a donut-shaped universe where traveling far enough in one direction brings you back to your starting point. In this scenario, the universe wouldn't need to be infinite, just finite yet unbounded, like a Pac-Man screen where exiting one edge means reappearing on the opposite side. The real headache is testing these ideas. Light hasn't had time to circle a hypothetical donut universe since the Big Bang, leaving us with no direct way to detect such loops. Yet subtle hints might lurk in the cosmic microwave background. If space is multiply-connected, identical patterns of temperature fluctuations could repeat like celestial wallpaper echoing across the sky. So far, searches for these ghostly duplicates have come up empty, but the hunt isn't over. Then there's the elephant in the room, inflation. The theory that the universe expanded exponentially in its first sliver of a second predicts a flat cosmos with staggering precision. But inflation also stretches spacetime so much that any primordial curvature becomes negligible, like smoothing out wrinkles on a balloon as it inflates. This leaves us questioning, is the universe truly infinite, or does it just look that way because we're trapped in our tiny pocket of smoothed-out space? Perhaps the most unsettling possibility is that infinity isn't just a mathematical quirk but a physical reality. An endless universe means there are infinite copies of Earth, infinite versions of you, and infinite variations of history playing out in the cosmic deep. It's a dizzying thought, one that challenges not just our cosmology but our very sense of place in existence. Until we crack the geometry of the cosmos, infinity remains the ultimate cosmic riddle, an endless question mark hanging over the stars. Hidden behind the dense curtain of stars and dust in the Milky Way's plane, something massive is tugging at our galaxy and thousands of others with irresistible gravitational force. This is the Great Attractor, a mysterious region of space roughly 250 million light-years away that's pulling entire galaxies toward it at breakneck speeds. Picture a cosmic whirlpool, its currents dragging everything in its reach toward an unseen center. Even our own Milky Way, along with the Andromeda Galaxy and the rest of the local group, is racing toward it at over 2 million kilometers per hour. But what exactly lies at the heart of this gravitational enigma? The frustrating answer, we don't fully know because the Milky Way's dusty galactic disk blocks our view, leaving the Great Attractor shrouded in cosmic censorship. Early observations in the 1970s and 80s revealed something bizarre. Galaxies in our corner of the universe weren't just drifting apart with the general expansion of space. They were all streaming toward a specific point in the constellation Centaurus, like iron filings drawn to a hidden magnet. At first, astronomers assumed it must be a colossal cluster of galaxies, perhaps a dense knot of matter with enough gravity to sway an entire cosmic neighborhood. But when they peered through the galactic haze with infrared and radio telescopes, they found something even stranger. the mass of visible galaxies in that region couldn't possibly account for the sheer strength of the pull. There had to be something more, something invisible lurking in the shadows. This is where the plot thickens. The Great Attractor might not be a single, monolithic structure, but part of something far grander, the Laniakea supercluster. Revealed in 2014 through painstaking mapping of galaxy motions, Laniakea Hawaiian for immeasurable heaven is a vast cosmic filament spanning 500 million light-years, containing roughly 100,000 galaxies. Within this web, the Great Attractor acts like a gravitational anchor, a dense node where multiple galactic tendrils converge. Picture a mountain at the center of a swirling river system, directing the flow of water across an entire continent. That's the role the Great Attractor seems to play, a pivotal point in Laniakea's sprawling geography. Yet even Laniakea's immense mass doesn't fully explain the velocities of galaxies caught in this flow. Some scientists speculate an even larger force might be at work, the Shapley supercluster, a monstrous assembly of galaxies 650 million light-years away, pulling both the Great Attractor and us toward it like a cosmic puppet master. Others wonder if dark matter clumped in unimaginable densities could be amplifying the Great Attractor's grip, warping space-time in ways we can't yet measure. The real challenge is observation. To glimpse the Great Attractor's core, astronomers must rely on wavelengths that pierce the Milky Way's dust like X-rays or infrared light. Missions like NASA's Chandra X-ray Observatory have revealed clusters of galaxies colliding in this region, their hot gas glowing like cosmic streetlights in the dark. But whether these are the true source of the attraction or just signposts pointing deeper into the mystery remains unclear. What's certain is this: the Great Attractor forces us to confront how little we understand about the large-scale structure of the universe. It's a reminder that even as we map the cosmos, vast, unseen forces are at work sculpting the paths of galaxies, steering the motion of everything we can see, and perhaps hiding answers that could rewrite our place in the cosmic web. Until we solve its riddle, the Great Attractor will remain one of the universe's most tantalizing blind spots, a gravitational siren calling us toward the unknown. One moment, a star burns bright in the night sky. The next, it's gone without so much as a cosmic goodbye. That's exactly what happened with Kinman's dwarf, a distant star in the constellation Aquarius that simply vanished. Astronomers had been studying this luminous blue variable star, a rare hypergiant breed prone to violent outbursts, for decades. Then, between 2009 and 2019, it disappeared from telescope images without any trace of a supernova, black hole, or debris cloud. Poof, gone. It's as if the universe hit the delete button, leaving behind one of modern astronomy's most haunting cold cases. Theories abound, and none of them are comforting. One possibility: a failed supernova where a massive star collapses directly into a black hole without the usual fireworks. Normally, when giant stars die, they go out with a bang, exploding in a supernova so bright it can outshine entire galaxies. But in rare cases, theorists suggest, a star might implode so abruptly that the explosion gets smothered by its own gravity, like a firework dud sinking into a black hole's event horizon. The result: a star winks out of existence, leaving behind only gravitational ripples and a lot of confused astronomers. Then there's the dust veil hypothesis. Some stars, especially unstable giants like Kinman's dwarf, experience extreme eruptions that eject massive amounts of gas and dust. If enough material gets thrown out in a short time, it could form a thick cocoon around the star, blocking its light entirely from our view. Imagine a car's headlights vanishing in a blizzard, except here, the blizzard is a self-made shroud of stellar debris. The catch: even this wouldn't fully explain the total disappearance. Dust clouds still emit infrared radiation, and so far, telescopes haven't picked up the expected heat signature. Could it be something stranger? A few bold hypotheses suggest these stars might collapse into exotic objects like quark stars, ultra-dense bodies made of subatomic particles that straddle the line between neutron stars and black holes. Others float the idea of dark stars, powered not by nuclear fusion but by annihilating dark matter, though evidence for such objects remains purely theoretical. The unsettling truth is that stars like Kinman's dwarf force us to confront how much we don't know about stellar deaths. Our models are built on the stars that follow the rules, the ones that explode or fade predictably. The outliers, the vanishings, reveal the gaps in our understanding, like shadows moving behind a curtain. Every time a star disappears without explanation, it's a humbling reminder. The universe still holds secrets that defy even our most careful observations. And until we solve them, the cosmos keeps its most dramatic exits a mystery. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a signal so powerful and unusual it made an astronomer scrawl, "Wow." In red pen on the data printout, that single word gave the "wow" signal its name, and 45 years later, it remains perhaps the most tantalizing and frustrating hint that we might not be alone in the universe. For 72 seconds, the Big Ear telescope at Ohio State University, locked onto a narrowband radio, burst exactly at the frequency of hydrogen, the most common element in the cosmos. This wasn't random static or earthly interference. It was a focused, intense transmission resembling the kind of deliberate beacon an advanced civilization might send. Then, just as suddenly as it appeared, it vanished, never to be heard again despite decades of follow-up searches. The signal's intensity spiked and fell in a way that matched Earth rotation, suggesting a fixed cosmic source rather than a passing satellite or aircraft. And its frequency, a tantalizing 1,420 MHz, a protected band where earthly transmissions are banned, right where scientists had predicted an alien signal might appear. So what could it have been? The leading natural explanation points to a pair of comets, 266P and 267P, which happened to be passing through that patch of sky unseen in 1977. Hydrogen clouds around these icy wanderers might emit similar radio waves, but here's the catch. Those comets weren't discovered until years later, and their emissions have never matched the wow signal's strength or signature. Other theories suggest a rogue astrophysical event, like a never-before-seen stellar flare or a chance alignment of cosmic phenomena, but nothing quite fits. Then there's the possibility that still makes hearts race, the idea that it was artificial. If the signal came from a civilization even slightly more advanced than ours, they could have built a transmitter powerful enough to briefly outshine natural cosmic radio sources. The signal's narrowband nature is particularly suspicious. Natural cosmic noise tends to be broadband, while purposeful transmissions focus energy into tight frequencies for efficiency. And the fact that it hasn't repeated, that could mean anything: a one-time beacon, a malfunctioning alien satellite, or even a message we were never meant to decode. The frustration for SETI researchers is that we'll likely never know for sure. Without a repeat signal or precise location data, the WOW signal floats in limbo, too compelling to dismiss, too elusive to confirm. It's become a ghost in the machine of cosmic exploration, a whisper from the void that challenges us to keep listening, to keep wondering. Whether it was a cosmic fluke or the first hello from another mind in the dark, one thing's certain: it's the closest we've ever come to feeling like we're not alone in this vast, silent universe. And that makes it a mystery worth chasing to the stars. Water covers 70% of Earth's surface, but its origin is one of planetary science's greatest head-scratchers. How did a barren, molten rock transform into the blue oasis we call home? The leading theories split into two camps. One looks to the heavens, the other to the depths beneath our feet. The cosmic delivery theory suggests Earth's water hitched a ride on icy comets and asteroids during the solar system's chaotic early days. These frozen time capsules bombarded our young planet, melting on impact and filling ancient basins with the first primordial seas. Evidence comes from meteorites like those found in Antarctica, which contain water molecules chemically similar to Earth's oceans. But here's the snag: comets from the distant Kuiper belt and Oort cloud, like Halley and Hale-Bopp, have water with twice the deuterium, a heavy hydrogen isotope, compared to Earth's seawater. That mismatch throws a wrench in the idea that all our water arrived pre-packaged from deep space. Then there's volcanic outgassing, the idea that Earth cooked its own water from scratch. In this scenario, hydrogen trapped in the planet's mantle bonded with oxygen from molten rock, spewing steam through countless eruptions that condensed into rain over millions of years. Support comes from modern volcanoes, which still belch water vapor today. But this theory has its own puzzle. If all Earth's water came from within, why do we see deuterium ratios that suggest a mix of sources? The answer might lie in a cosmic balancing act. Some asteroids, particularly those from the outer asteroid belt, carry water with deuterium levels eerily close to Earth. Missions like Japan's Hayabusa 2 sampled these space rocks, revealing water-rich minerals that could have seeded our oceans without skewing the deuterium math too far. Meanwhile, noble gases trapped in Earth's mantle hint at ancient volcanic contributions, suggesting both theories might be right: part delivery, part homegrown. But the plot thickens when we zoom out. Mars has water locked in polar ice and buried groundwater, yet its deuterium ratio is wildly different. Even the Moon, long thought bone dry, hides water molecules in shadowed craters with their own isotopic quirks. These differences suggest water's journey isn't just about where it came from, but when it arrived. Early solar system bombardments versus late-stage asteroid showers, mixed with planetary geology, could create the unique cocktail we see on each world. The stakes are higher than just solving Earth's mystery. If asteroids delivered key ingredients for life here, they might have done the same on exoplanets light years away. Or if rocky worlds naturally brew their own water through volcanism, the universe could be far wetter and more habitable than we ever imagined. Every drop in our oceans carries echoes of this ancient puzzle, a reminder that the simplest things, like water, often hold the deepest secrets. Far beyond Neptune, where the sun is just a dim speck in the perpetual twilight, something massive may be lurking in the frozen dark. Astronomers call it Planet 9, a hypothetical world up to 10 times heavier than Earth, prowling the solar system's outer reaches on an orbit so vast it could take 20,000 years to complete a single lap around the sun. This isn't just wild speculation. It's a theory born from bizarre patterns in the orbits of distant icy bodies, cosmic breadcrumbs that hint at a hidden architect reshaping the outer solar system from the shadows. The clues first emerged in 2014, when astronomers Chad Trujillo and Scott Shepard noticed something odd about Sedna and a handful of other extreme trans-Neptunian objects. These frozen worlds, drifting hundreds of astronomical units from the Sun, shared an unexpected trait: their elongated orbits all clustered in one direction, as if nudged by an unseen hand. Then in 2016, Caltech researchers Konstantin Batygin and Mike Brown crunched the numbers, revealing the odds of this alignment happening by chance were a mere 0.2%. Their simulations showed only one plausible explanation: a distant, super-Earth-sized planet, its gravity herding these objects like an invisible sheepdog. But finding Planet 9 is like searching for a black cat in a coal cellar. At an estimated distance of 400 to 800 astronomical units, it would reflect so little sunlight that even our most powerful telescopes strain to spot it. The Vera Rubin Observatory, set to begin sweeping the skies in 2025, might finally have the sensitivity to catch its faint glow, but for now, the hunt relies on indirect methods. Astronomers meticulously track the motions of far-flung objects, looking for subtle orbital anomalies that could betray the giant's position. Every newly discovered trans-Neptunian object like the bizarrely tilted goblin or the ultra-distant, far, far out adds another data point to the celestial treasure map. Skeptics argue the gravitational anomalies could stem from a swarm of smaller objects or even statistical flukes in our still sparse sensors of the outer solar system. Others propose wilder alternatives, like a primordial black hole no larger than a grapefruit but with the mass of a planet, lurking undetected. Yet Planet Nine's proponents counter with an intriguing detail. Their models predict exactly where such a world should be, and new discoveries keep falling eerily close to those predicted orbits. If it's real, Planet Nine could rewrite solar system history. Perhaps it's a rogue planet snatched by the sun's gravity in our star's chaotic youth, or a failed core of a gas giant ejected during Neptune's outward migration. Its existence would explain other puzzles too, like why the solar system's plane tilts 6 degrees relative to the sun, or why some distant objects orbit perpendicular to the rest. The search has become a modern-day astronomical odyssey, blending cutting-edge math with old-fashioned sky-scanning patience. Every night, telescopes peer deeper into the void, wondering if the next speck of light might solve the mystery or deepen it. Until then, Planet Nine remains both a tantalizing possibility and a reminder of how much we still don't know about our own cosmic backyard. The sun's surface blazes at around 5,500 degrees Celsius, hot enough to vaporize steel instantly. Yet just above it, in the wispy outer atmosphere called the corona, temperatures skyrocket to over 1 million degrees. This bizarre thermal inversion, known as the coronal heating problem, defies all basic intuition. If you held your hand near a campfire, you wouldn't expect the air 10 feet above it to be 200 times hotter than the flames. So why does the sun break all the rules? The answer might lie in magnetism, the sun's invisible puppet master. Our star is a writhing ball of plasma, with magnetic fields constantly twisting, snapping, and reconnecting like cosmic rubber bands. One leading theory points to magnetic reconnection, a process where tangled field lines explosively realign, releasing enormous energy in solar flares and coronal loops. Picture two magnets snapping together with such force that they launch a burst of heat outward. These nanoflares, smaller versions of their dramatic solar flare cousins, could be constantly peppering the corona, keeping it sizzling like a skillet over a steady flame. But there's a rival idea: wave heating. The sun's churning interior generates waves similar to seismic ripples, but powered by magnetism instead of rock. As these waves travel upward, they grow more intense, eventually crashing like ocean surf in the corona and dumping their energy as heat. Some researchers argue it's a mix of both processes, with magnetic reconnection dominating near-active sunspots while waves heat quieter regions. The challenge: proving any of this from 93 million miles away. NASA Parker Solar Probe, humanity's first mission to touch the sun, flies through the corona itself, enduring extreme heat to measure magnetic fields and particle speeds. Early data reveals bizarre switchbacks, sudden zigzags in the sun's magnetic field that could be dumping energy into the corona like a cosmic slingshot. Meanwhile, telescopes like the Daniel K. Inau Solar Telescope capture ultra-sharp images of magnetic braids thinner than Manhattan, snapping and reforming in real time. Solving this puzzle isn't just about understanding our own star. The same processes might drive the scorching atmospheres of other stars, influence space weather that threatens satellites, or even reveal new ways to harness plasma energy here on Earth. Until then, the corona remains a blazing enigma, a reminder that even the most familiar objects in the sky can hide secrets that defy our expectations. What if our universe is just one page in an infinite cosmic library? This is the tantalizing premise of the multiverse theory, the idea that our reality might be one of countless others, each with its own unique laws of physics, constants, and maybe even versions of you. While it sounds like science fiction, some of the world's leading physicists take this idea seriously. thanks to clues buried in quantum mechanics, cosmology, and string theory. Start with cosmic inflation, the theory that our universe underwent a mind-bending expansion in its first moments. Some versions suggest this inflationary process might not have stopped everywhere. Instead, pockets of space could continue inflating eternally, spawning new universes like bubbles in an endlessly boiling pot. Each bubble universe would cool into its own distinct cosmos, with different physical constants, perhaps some where gravity is stronger, others where atoms never form, and rare ones like ours where life becomes possible. This eternal inflation scenario implies a multiverse so vast it makes our observable universe seem like a grain of sand on an endless beach. Then there's string theory's landscape problem. To unify quantum mechanics and gravity, string theory requires extra dimensions, tiny, curled-up shapes at every point in space. But the math allows for an astonishing number of possible configurations, perhaps 10 to the power of 500 variations. Each could correspond to a different universe with its own physics. Nobel laureate Steven Weinberg once suggested this might explain why our universe seems finely tuned for life. If every possible configuration exists somewhere, it's no surprise we find ourselves in one that allows galaxies, stars, and ultimately us. Quantum mechanics adds another layer. The many worlds interpretation proposes that every quantum measurement outcome splits reality into branching timelines. Choose tea over coffee, and another you in a parallel universe makes the opposite choice. While these branches aren't separate universes in the cosmological sense, they hint at how deeply multiverse thinking permeates modern physics. The catch: no direct evidence supports any of this. Multiverses are, by definition, beyond our observational horizon. Critics argue this makes the theory unfalsifiable, more philosophy than science. Others counter that indirect signatures might exist, like unusual patterns in the cosmic microwave background from collisions with other bubble universes, or anomalies in the distribution of galaxies. So far, none have been found. Philosophically, the multiverse challenges our very notion of reality. If an infinite number of universes exist, does that diminish the significance of our own? Or does it elevate the wonder that, against all odds, we find ourselves in a cosmos where we can even ponder such questions? Whether the multiverse remains a speculative dream or becomes a cornerstone of physics, it pushes us to think bigger, not just about what exists but about what could. In the vast, silent expanse of the solar system, two tiny spacecraft, Pioneer 10 and 11, were supposed to be coasting effortlessly through the void, their trajectories as predictable as clockwork. Yet something strange happened as they ventured beyond the asteroid belt. An invisible force, barely detectable but undeniable, was tugging at them, slowing them down in ways Newton's laws couldn't explain. This was the Pioneer anomaly, a cosmic whodunit that puzzled scientists for decades and still serves as a humbling reminder of how much we don't understand about the forces shaping our universe. The numbers didn't add up. By the time Pioneer 10 reached Saturn's orbit, it was lagging behind its projected path by hundreds of thousands of kilometers, a discrepancy caused by an unaccounted deceleration roughly 10 billion times weaker than Earth's gravity. At first, researchers dismissed it as a fluke, perhaps an error in tracking or onboard systems. But when Pioneer 11 exhibited the same mysterious drag, the scientific community had to confront an unsettling possibility. Either our understanding of gravity was incomplete, or some unseen factor was nudging these probes off course. The prime suspect: heat. Every spacecraft emits a faint thermal glow from its power systems, and Pioneer's design meant most of that radiation leaked asymmetrically, more from its rear than its sides. The idea was simple. Photons carrying this heat energy might have acted like microscopic thrusters in reverse, providing just enough push to explain the anomaly. Computer models suggested this could account for up to 70% of the deceleration. But here's where things got messy. Even after painstakingly reconstructing Pioneer's heat signature and adjusting for every conceivable variable, a stubborn fraction of the slowdown remained unexplained. Some researchers floated wilder ideas, modified gravity theories, unseen dark matter interactions, or even exotic drag from the quantum vacuum. The real lesson of the Pioneer anomaly isn't just about one unsolved puzzle, it's about the fragility of precision in deep space. Modern missions like New Horizons, which flew past Pluto, now account for minuscule forces that would have been ignored in Pioneer's era. Engineers tweak spacecraft designs to balance thermal emissions, and navigators pass telemetry data for the faintest irregularities. Yet the anomaly lingers as a ghost in the data, a whisper that even our most trusted equations might hide blind spots. What makes this mystery so enduring is its duality. It's both mundane and profound. On one hand, the answer might be as simple as a few errant watts of heat, a testament to how easily overlooked details can ripple into major scientific questions. On the other, it hints at the possibility that gravity itself behaves differently in the outer solar system's quiet depths, a frontier where our physics might need rewriting. Until the next generation of deep space probes ventures into that darkness, the Pioneer anomaly remains open, a tiny but nagging reminder that the universe often saves its quietest surprises for those who look closest. Turn the moon around in your mind for a moment. The face it always shows us, the familiar, smooth plains we see every night, is just one side of the story. The far side, forever hidden from Earth's view until satellites first revealed it in the 1950s, is a shockingly different world. Where our side has vast, dark seas of hardened lava, the far side is a rugged, crater-pocked wasteland, its surface resembling a battlefield from some ancient cosmic war. This stark duality isn't just a curiosity, it's a planetary science puzzle begging the question, how could two halves of the same world end up so fundamentally different? One leading theory points to Earth's gravitational bullying during the moon's infancy. Early in their cosmic dance, the moon likely spun faster and orbited much closer to our planet. Over time, Earth's gravity locked one side permanently toward us, a phenomenon called tidal locking, but the process may have done more than synchronize rotations. The same tidal forces that stretch oceans could have stretched the moon's molten mantle, keeping the near side geologically warm and active while the far side cooled and hardened. Picture holding a water balloon. Squeeze one side and the other bulges outward. If Earth's gravity kept the near side pliable, lava might have erupted more easily there, flooding impact basins and creating the smooth plains we see today. Meanwhile, the far side, shielded from this kneading effect, became a frozen relic of the moon's violent early bombardment. Then there's the impact hypothesis, a cataclysmic collision that reshaped the moon's fate. Computer simulations suggest a second, smaller moon might have once shared Earth's orbit, eventually smashing into our moon's far side at glacier-like speeds. This splat wouldn't have carved a crater but instead spread debris like thick pancake batter, adding miles of crust to the far side while leaving the near side untouched. Supporting this idea, gravity maps reveal the far side's crust is substantially thicker, up to 60 miles deep compared to the near side's 30. That extra armor could have prevented magma from breaching the surface as often, leaving the terrain scarred and untouched by volcanic resurfacing. But the plot thickens with chemistry. Lunar samples show the near side is rich in radioactive elements like uranium and thorium, which generate heat as they decay. These elements seem concentrated in a region called the Procellarum creep terrain, a vast, heat-producing engine that might have supercharged volcanic activity on the near side while the far side remained geologically silent. How this asymmetry arose is still debated. Was it random luck during the moon's formation, or did Earth's gravity funnel these heavy elements toward the side it constantly tugged? The moon's split personality offers more than just a history lesson. It's a window into the chaotic processes that shape all rocky worlds. Every crater on the far side is a fossilized record of the solar system's violent youth, while the near side's smooth plains whisper of hidden reservoirs of heat and molten rock. Future missions like China's Chang landers sampling the far side's unique geology may finally crack this two-faced mystery. Until then, our celestial neighbor remains a constant reminder sometimes what's right in front of us is only half the story. Imagine a planet untethered from any star, drifting through the eternal night of interstellar space. No sunrise, no sunset, just perpetual darkness stretching on for eons. These are rogue planets, cosmic nomads ejected from their home solar systems or born in the cold isolation of interstellar gas clouds. Unlike the planets we know, they don't orbit a star. They're free-floating ghosts, invisible to traditional detection methods, yet astronomers now suspect they might outnumber stars in our galaxy by a staggering margin. How does a planet end up alone in the void? The most common scenario is a gravitational catastrophe. In young star systems, planets jostle for position, and sometimes one gets too close to a sibling, especially a gas giant. A passing interaction can slingshot a planet outward with enough force to escape its star's gravity entirely, flinging it into the abyss. Simulations suggest this happens more often than we once thought, with some studies estimating that for every star in the Milky Way, there could be 20 or more rogue planets careening through the darkness. But there's another, even stranger possibility. Some rogue planets might form on their own. Dense pockets within interstellar gas clouds could collapse under their own gravity, birthing planets without ever hosting a star. These failed stars, too small to ignite fusion but too massive to be mere asteroids, blur the line between planet and cosmic orphan. Spotting these lone wanderers is like searching for a black cat in a pitch-black room. Without starlight to illuminate them, they're nearly invisible. Astronomers rely on two clever tricks: microlensing and thermal signatures. When a rogue planet passes in front of a distant star, its gravity bends the star's light like a lens, creating a brief brightness spike that betrays its presence. Meanwhile, young rogue planets still glow faintly with residual heat from their formation, detectable in infrared by telescopes like NASA's upcoming Nancy Grace Roman Space Telescope. Already, surveys have uncovered candidates like CFBD SIR 2149-0403, a rogue planet drifting just 100 light-years away, and others that may outnumber known exoplanets. The most tantalizing question: could rogue planets harbor life? It sounds implausible. No sunlight means no photosynthesis, the foundation of Earth's food webs. But beneath icy shells, tidal forces or radioactive decay might maintain subsurface oceans, just like Jupiter's moon Europa. Hydrothermal vents could power ecosystems in eternal darkness, while thick hydrogen atmospheres might trap enough geothermal heat to create habitable pockets. Some rogue planets could even have moons with atmospheres warmed by the planet's residual heat, creating bizarre oases adrift between the stars. If life exists on these worlds, it would be utterly alien, evolving without day or night, perhaps in slow-motion biospheres powered by chemistry rather than sunlight. The sheer number of rogue planets raises the mind-bending possibility that life might be far more common in the galaxy than we imagine, just not where we expected to find it. These solitary worlds challenge our definitions of planets, habitability, and even the boundaries of life itself. They remind us that the cosmos is full of shadows hiding secrets we're only beginning to glimpse, and that sometimes the most fascinating stories unfold in the darkest corners of space. For over 3 billion years, life on Earth was content playing a simple game, single-celled organisms drifting through ancient seas, barely changing from one eon to the next. Then, in what feels like a cosmic blink, everything exploded. The Cambrian period, roughly 540 million years ago, saw life undergo a radical transformation unlike anything before or since. Within just 20 million years, a mere heartbeat in geological time, the planet went from hosting basic multicellular creatures to teeming with complex animals sporting eyes, skeletons, and behaviors straight out of a sci-fi bestiary. This Cambrian explosion remains biology's greatest magic trick, and the question isn't just how it happened, but why then. One of the wildest theories points to the stars. Gamma-ray bursts, the universe's most powerful explosions, could have played an unlikely role in Earth's biological revolution. When a massive star collapses or neutron stars merge, they unleash beams of radiation so intense they can sterilize planets light years away. A nearby gamma-ray burst hitting Earth during the Precambrian might have done something counterintuitive. Instead of wiping life out, it could have cleared the deck. By stripping away much of the ozone layer, the burst would have allowed intense ultraviolet radiation to penetrate shallow waters, killing off vast swaths of surface-dwelling microorganisms. This sudden thinning of competition could have opened ecological niches, giving surviving organisms room to experiment with radical new body plans. But cosmic triggers aren't the only suspects. Earth itself was undergoing dramatic changes. Oxygen levels, which had been creeping upward thanks to photosynthetic bacteria, may have finally crossed a critical threshold, rising from less than 1% of the atmosphere to near modern levels. This oxygen surge could have powered energy-hungry innovations like predator-prey arms races, where hard shells and complex organs became survival necessities. Meanwhile, shifting continents and rising sea levels created vast shallow seas, ideal laboratories for evolutionary experimentation. Then there's the genetic angle. Some scientists argue the Cambrian explosion was less about environment and more about unlocking a biological toolkit, the evolution of Hox genes. Master switches that dictate body plans might have allowed organisms to suddenly try out wildly different forms, like a child discovering they can rearrange building blocks into endless configurations. Combine this with chemical signaling between species, and you have a recipe for explosive diversification. The Cambrian explosion might even rewrite how we search for alien life. If cosmic events like gamma-ray bursts can catalyze complexity, then planets in certain galactic neighborhoods, those with occasional stellar cataclysms, could be more likely to host advanced life than quieter regions. Or perhaps Earth's perfect storm of oxygen, geology, and genetics was a 1 in a trillion fluke. Until we find fossils on Mars or detect biosignatures on distant exoplanets, this evolutionary fireworks show remains one of nature's best-kept secrets, a reminder that sometimes life doesn't just evolve. It erupts. Think of the void between stars as a blank canvas, except this canvas isn't blank at all. The vacuum of space, often imagined as a perfect nothingness, is actually a seething quantum frenzy, where particles flicker in and out of existence so fast they defy everything we know about reality. This isn't science fiction, it's a cornerstone of quantum field theory, and it means that empty space is anything but empty. At the heart of this revelation are quantum fluctuations, tiny, spontaneous disturbances in the fabric of reality itself. According to Heisenberg's uncertainty principle, even in a perfect vacuum, energy isn't static. Instead, it fluctuates unpredictably, allowing pairs of virtual particles, one matter, one antimatter, to pop into existence briefly before annihilating each other. These particles aren't just theoretical. They've been detected indirectly through phenomena like the Lamb shift, where subtle changes in atomic energy levels reveal their ghostly influence. Picture a calm lake surface suddenly erupting with microscopic bubbles that vanish almost instantly. That's the quantum vacuum, endlessly bubbling with ephemeral creation and destruction. But how do we know this chaos is real? Enter the Casimir effect, a startling demonstration of quantum weirdness in action. In the 1940s, physicist Hendrik Casimir predicted that if you placed two uncharged metal plates extremely close together in a vacuum, they'd be pushed toward each other by an invisible force. The reason: virtual particles outside the plates exert more pressure than those between them, where only certain wavelengths can fit. The result: a measurable, irresistible pull, proof that empty space is alive with transient energy. Modern experiments have confirmed this effect down to nanometer scales, turning a theoretical curiosity into one of quantum physics' most tangible triumphs. The implications are mind-bending. If virtual particles can borrow energy from the vacuum, could we harness it? Theoretically, yes, though the energy, loan, must be repaid almost instantly, making practical extraction a nightmare. Some speculate advanced civilizations might manipulate these fluctuations for propulsion, bending space-time itself. Others see them as key to understanding dark energy, the mysterious force accelerating the universe's expansion. Could vacuum energy be driving cosmic acceleration? The math suggests its predicted strength is 10 to the power of 120 times greater than observed dark energy, a discrepancy so vast it's called the worst theoretical prediction in physics. Yet the vacuum's secrets go deeper. During cosmic inflation, quantum fluctuations stretched to macroscopic scales, seeding the density variations that eventually became galaxies. In a very real sense, the structure of the universe was born from these quantum whispers. Even black holes aren't immune. Their event horizons amplify virtual particle pairs, leading to Hawking radiation, the slow evaporation that might one day erase them from existence. So next time you gaze at the night sky, remember, the void isn't void at all. It's a dynamic, writhing stage where particles dance in and out of reality, shaping everything from atoms to galaxies. The true wonder isn't just that space teems with hidden energy, it's that we've begun to decode its language at all. Watch a spinning ice skater pull their arms in, and they whirl faster. A perfect demonstration of how gravity and motion should work. Now look at a galaxy like the Milky Way and something bizarre happens. Stars on the outer edges orbit just as fast as those near the center, as if the skater's arms didn't change their speed at all. This cosmic defiance of Newton's laws is one of astronomy's most persistent puzzles, and it's forced scientists to propose two radical solutions. Either the universe is packed with invisible matter we can't see, or our understanding of gravity itself is fundamentally flawed. Let's start with the dark matter explanation. When astronomers first mapped the rotation curves of spiral galaxies, they expected stars farther from the galactic center to move slower, just like Pluto crawls compared to Mercury. Instead, they found stars whipping around at nearly the same speed regardless of distance. The only way this makes sense: a massive, invisible halo of dark matter must envelop each galaxy, its gravity propping up those outer stars like an unseen hand guiding a merry-go-round. Simulations back this up. Without dark matter's extra tug, galaxies would fly apart, their stars scattering into the void. Yet after decades of hunting, we still can't directly detect this mysterious substance, leaving a glaring gap in the theory. Enter modified Newtonian dynamics, proposed in the 1980s by physicist Mordechai Milgrom. MND suggests we don't need dark matter at all. Instead, gravity might behave differently at extremely low accelerations, like those experienced by stars on a galaxy's fringe. Tweaking Newton's equations to account for this could explain the rotation curves without invoking invisible particles. Think of it like this: if gravity's pull weakens less than expected over vast distances, outer stars would naturally orbit faster than classical physics predicts. MND appeal: it elegantly matches observed rotation curves for many galaxies without extra ingredients. But MND has its own Achilles heel. While it nails galaxy rotations, it struggles with cosmic phenomena like the bullet cluster, where colliding galaxies leave visible matter and gravitational effects visibly separated, a smoking gun for dark matter's existence. It also falters when simulating the universe's large-scale structure, where dark matter's gravitational scaffolding perfectly explains how galaxies cluster into filaments and voids. The debate rages on, with each camp marshalling evidence. Dark matter proponents point to upcoming experiments like LUX Zeppelin, hunting for elusive dark particles deep underground. Meanwhile, MUN supporters refine their models, searching for a unified version that might one day crack cosmology's toughest cases. What's at stake isn't just an academic disagreement, it's a choice between rewriting our inventory of the cosmos or rewriting the laws that govern it. Until one side clinches the proof, galaxies will keep spinning mysteries faster than our theories can keep up. Imagine the universe as a perfectly shuffled deck of cards. No matter how you deal them, there should be no hidden pattern, no secret order. That's the cosmological principle in a nutshell, the idea that on the largest scales, the cosmos is smooth, uniform, and essentially the same in every direction. But when scientists mapped the cosmic microwave background, the afterglow of the Big Bang, they stumbled upon something that made them question everything. A bizarre, unexpected alignment in the fabric of spacetime itself, so unsettling they called it the axis of evil. This ominous-sounding name isn't hyperbole, it's a genuine crisis for cosmology. The cosmic microwave background, or CMB, is our most pristine snapshot of the infant universe, a fossilized light pattern from when the cosmos was just 380,000 years old. According to theory, the temperature fluctuations in this radiation should be randomly distributed like static on an old TV. But when researchers analyzed data from satellites like WMAP and Planck, they found a spine-tingling anomaly. The hot and cold spots weren't scattered chaotically. Instead, they seemed to loosely align along a specific axis, as if the universe had a hidden, preferred direction. It's like tossing confetti into the air only to watch it fall into a perfect spiral, a defiance of probability so glaring it threatens to upend our understanding of the universe's fundamental nature. The implications are staggering. If the CMB's alignment is real and not some fluke, it challenges the cosmological principle at its core. Maybe the universe isn't as homogeneous as we thought. Perhaps there's a grand structure, a cosmic frame of reference, that stretches across the observable universe, influencing everything from galaxy clusters to the CMB itself. Some theorists have speculated wildly. Could this axis be a relic of primordial spacetime distortions from before the Big Bang, or evidence of a sibling universe brushing against ours in a higher dimensional multiverse? The most unsettling possibility, that we're seeing the fingerprints of something entirely unknown, a force or structure that rewrites the rules we thought were universal. Skeptics argue it might just be a statistical illusion or an artifact of how we process the data. After all, the universe is vast, and even random distributions can sometimes look ordered. But the axis of evil has stubbornly persisted across multiple missions and independent analyses, refusing to vanish under scrutiny. Right now, the smart money is on an unknown systematic error, some subtle bias in measurement or foreground interference we haven't accounted for. Yet the longer this anomaly lingers, the harder it is to ignore the unnerving thought. What if the universe really does have a hidden axis, a cosmic north we never knew existed? Until we crack this enigma, the axis of evil stands as a quiet rebellion against our most cherished assumptions, a whisper that the universe might still be keeping its deepest secrets. Black holes aren't just cosmic vacuum cleaners, they're information shredders, or so we thought. According to classical physics, anything crossing a black hole's event horizon vanishes forever, taking its information, the unique arrangement of particles that made it into oblivion. But quantum mechanics throws a wrench in this idea. In the quantum realm, information can't be destroyed any more than you can unmix paint back into its original colors. This clash between gravity and quantum theory is the infamous black hole information paradox, a puzzle that's haunted physicists for decades and forced some of the brightest minds to question the fundamental nature of reality. Enter Hawking radiation, the brilliant insight that rocketed Stephen Hawking to fame. In the 1970s, Hawking realized black holes aren't completely black. Quantum fluctuations near the event horizon allow pairs of virtual particles to pop into existence. Normally, these particles annihilate each other instantly, but if one falls into the black hole while the other escapes, the whole loses energy over time, slowly evaporating. Here's the problem. Hawking's math suggested this radiation is completely random, carrying no information about what fell in. If the whole evaporates entirely, that information is erased forever, a direct violation of quantum mechanics' sacred rule that information must be preserved. The debate reached a boiling point in 2004 when Hawking himself reversed his stance, conceding that information must escape somehow. But how? One clue arrived with the discovery of soft hair, a whimsical term for subtle imprints left on a black hole's event horizon. Imagine dipping a finger into water. The ripples preserve a faint memory of the disturbance. Similarly, when particles fall into a black hole, they might alter its gravitational and electromagnetic fields in infinitesimal ways, encoding data in these hairs like cosmic braille. As the black hole radiates, this information could theoretically leak back out, woven into the seemingly random Hawking particles. Recent breakthroughs in quantum gravity have added tantalizing layers to the story. The holographic principle suggests all the information swallowed by a black hole isn't lost inside but smeared across its two-dimensional surface, like a hologram storing 3D data on a flat screen. String theory takes it further, proposing that black holes are tangled knots of vibrating strings, their quantum states preserving information even as the hole shrinks. Meanwhile, experiments with quantum computers simulate tiny black holes, tracking how information might scramble and re-emerge, a digital playground for testing these esoteric ideas. Yet mysteries linger. If information escapes, how does it defeat the event horizon's grip? Some theories invoke wormholes branching inside the black hole, funneling data to other universes. Others suggest time itself behaves differently near the singularity, allowing information to loop back unexpectedly. The truth might lie in a grander theory marrying quantum mechanics and gravity, one that redefines not just black holes but the fabric of spacetime itself. What's at stake isn't just academic. If information can't truly vanish, then reality is far more resilient and interconnected than we imagined. Every burned book, every dissolved star, every thought you've ever had might leave some indelible mark on the cosmos, encrypted in ways we're only beginning to decipher. Until we solve this paradox, black holes remain the ultimate cosmic locks, and we're still searching for the keys. Consider the very atoms in your body, the carbon in your bones, the oxygen in your lungs. Each exists because the universe's fundamental constants are dialed to impossibly precise values. Adjust the strength of gravity by just 1 part in 10 to the power of 40, and stars would never ignite. Tweak the nuclear force slightly and carbon, the backbone of life, wouldn't form in stellar furnaces. This razor-thin balance is known as the fine-tuning problem, and it's forced scientists to confront an unsettling question. Is the universe's perfection for life a staggering coincidence, or does it point to something deeper? One compelling answer lies in the anthropic principle, the idea that our very existence as observers shapes the reality we perceive. In its simplest form, it's a cosmic version of survivor bias. We couldn't ponder these constants if they weren't set to allow life. Imagine a puddle marveling at how perfectly its hole fits its shape, but this doesn't explain why such a puddle-friendly hole exists in the first place. Enter the multiverse. If infinite universes bubble into existence, each with randomly varying constants statistically, some will inevitably hit the life-permitting jackpot. We're simply in the one where the numbers lined up, no design required. Yet this statistical escape hatch raises its own riddles. For one, a multiverse is untestable by definition. Its other universes lie beyond our cosmic horizon. And if every possible constant combination exists, why does ours seem to occupy such a peculiarly fertile middle ground? Too weak, a strong nuclear force, and protons wouldn't bind. Too strong, and stars would burn out in seconds. Life exists in a Goldilocks zone not just for planetary conditions, but for the laws of physics themselves. Some physicists propose a third path. The constants aren't random but emergent, the result of deeper laws we haven't uncovered. String theory's landscape of possible universes suggests even fundamental constants might be environmental, like the freezing point of water depending on atmospheric pressure. Others speculate about a cosmic Darwinism, black holes acting as universe seeds, with each new iteration slightly tweaking the constants, favoring life-friendly versions over eons. Then there's the elephant in the room. Does fine-tuning imply a tuner? While science rightly avoids invoking design, the question lingers in philosophy. Even staunch atheists like physicist Fred Hoyle conceded that carbon's resonance, a freakishly precise match for stellar fusion, felt like a put-up job. Today, some researchers explore whether consciousness itself might play a role in shaping reality, an idea straddling quantum theory and metaphysics. The truth is, fine-tuning sits at a crossroads not just of physics but of meaning. Whether it's a multiverse lottery, an undiscovered physics, or something beyond our current paradigms, the answer will redefine not just our place in the cosmos, but what the cosmos fundamentally is. Until then, every atom in your body remains a whisper of this exquisite mystery, a universe that somehow, against all odds, learned to look back at itself. From the invisible grip of dark matter to the silent enigma of advanced alien civilizations, from the violent birth of our universe to its uncertain fate, these 30 questions are more than just cosmic curiosities. They're glaring signposts marking the edges of human knowledge, challenges that humble even our brightest minds. Every time we think we've unraveled one mystery, the universe reveals another layer waiting to be explored. Think about that for a moment. We've built telescopes that glimpse galaxies billions of light years away, sent probes across the solar system, and decoded the quantum fabric of reality. Yet the cosmos still holds secrets that defy our understanding. Dark energy accelerates the universe's expansion, but we don't know why. Black holes devour information, then maybe spit it back out in ways we can't yet fathom. Stars vanish without a trace, rogue planets drift in eternal night, and the moon hides two faces beneath a veil of ancient violence. These aren't just gaps in a textbook, they're invitations. Each unanswered question is a door waiting to be kicked open, a puzzle begging to be solved. Here's the beautiful part: these mysteries belong to all of us. You don't need a PhD to wonder why antimatter didn't wipe out existence, or to gaze at the night sky and question if we're truly alone. Every great discovery in history started with someone daring to ask, what if? Maybe the next leap won't come from a lab or a space agency. Maybe it'll start with you staring up at the stars, letting your imagination run wild. So let's keep questioning. Let's stay hungry for the unknown. Drop your favorite cosmic mystery in the comments, whether it's the wow signal's eerie whisper, the great attractor's hidden pull, or something we didn't even cover today. Because the universe isn't done surprising us, and the best chapters of this story, they're still unwritten.